Okay, welcome back to the next module. So, what we are going to cover in this is going to be another modality which is ultrasound imaging. Like I have said earlier, in this course you could actually take ultrasound, it is a standalone piece. You could actually take up ultrasound imaging module itself after probably the first introduction, right. But level of content is going to be at a introductory level. So, this cannot be a substitute for a full course in ultrasound imaging that can typically follow introductory material that is given here. So, to the best extent possible, I will still cover along the lines of what is covered in the textbook that we have been following. However, there are few material that you will find are also slightly different from what is described in this textbook. So, let us jump in. What is going to be the outline? The standard template for this course, we will maintain that, which is going to be, we will have a quick overview of the imaging modality followed by the physics of the modality, right. In this case it is ultrasound physics, and after covering extensively the ultrasound physics part of it, we will move over to the instrumentation and imaging equation, image quality. In fact, I am very hesitant to say we will cover all this. We will cover, meaning we will touch and go all of this, but it is going to be really more of alerting you that these are the concepts that will be involved, and you may have to go back and really read. If you want to work in ultrasound imaging, perhaps you should consider taking a further course in this. But what will be covered in this order, right, the level will allow you to compare probably if you have taken the previous modules, right, the X-ray, nuclear medicine, you will be able to relate back to see how this is completely different from what was covered there, okay. So, this will be only to that extent, it is not going to be very involved. Nevertheless, I hope you will find this interesting and beautiful modality with its own advantages and lot of challenges, that I hope you will take it with lot more interest and study by yourself a little more on this subject, okay. Let us start with overview. So, what we knew from before, right, in this subject, right, in this course, we have strived to answer this question. Each modality, what is it that we are trying to go after? The image, right, what is the fundamental or the physical property of the object that is captured in each of the different modalities. In that sense, here loosely we talk about measuring the reflectivity of tissue to sound waves. Remember, in X-ray based modalities we talked about attenuation, right, how the body, attenuation property to X-ray energy, the distribution of that is what we were trying to capture. In nuclear medicine we were talking about radioactivity, right, how is the radioactivity captured, and then said where is the source for this radioactivity and how much is the radioactivity coming from a location. So, we were trying to do a source localization of radioactivity in nuclear medicine. So, here in ultrasound imaging, loosely we could call this as reflectivity of tissue to sound waves. So, we need to understand what is sound wave, and then we can define little more rigorously what do we mean by reflectivity. But essentially you can appreciate here that this does not seem anywhere close to the other properties that we have covered so far. So, this is a newer information about the material, the object, okay. So, apart from this, right, we talked about distribution of mu. In X-ray we talked about structural imaging, and when it came to PET we were talking about nuclear activity, and essentially there also where the radioactivity is coming from, that was interpreted in relation to maybe in some physiology that is taking place. Here is in ultrasound, it gives you additional handle. It can also measure the velocity of the moving objects. I mean, what is moving inside the body? Mostly blood, right. So, we want to see blood flow. Can we visualize the velocity of blood flow, right? Distribution of the velocities. These are very powerful aspects, right? So, ultrasound gives you a view using what we call as Doppler principle. So, we will cover intro on Doppler principle as well in the physics, but this is a unique aspect that we have not covered so far, right? Whatever we did in X-ray imaging and PET nuclear medicine, the two properties both for the structure or the anatomical image that you are going to see in ultrasound and some of these like blood flow imaging or blood velocity imaging, these are not really directly obtained in the modalities that we covered so far. So, this is a new information that we are getting, that itself is a very powerful, right? You are using a newer modality, you get to see, right? You get to see new information about the target object. So, again comparatively here there is no radiation, right? So, compared to your previous modality that we have covered so far, there is no radiation and also it is completely non-invasive. Okay. So, you are going to sit from outside and see what is inside the body, right. Of course, in some cases remember we talked about sending a camera and like minimally invasive, if you would call it, through the natural orifice. Like that here also you can send an ultrasound probe and you can do it, but it is still considered non-invasive. Okay. It is safe, of course no radiation, no ionization, so it is considered safe. Fast, what do we mean by fast? Very qualitative. Fast essentially saying that you can see the image as they are probing, unlike your CT or X-ray where we were talking about minutes that came down to seconds, and then you have a room adjacent where you have to be safe and the computer generates the image. Here actually the patient, right, you could actually see your own image while they are doing, okay, and so it is also inexpensive. Of course, this is in relative to the other modalities that we have talked so far. So, it has a lot of advantages, it gives you new information, right. So, nothing is, if this can do everything, there is no need for the other modalities, but like I told you, the whole field, there is always a give and take, there is a trade off. So, not, if you look at the image quality, right, in terms of your signal to noise ratio or contrast to noise ratio, is typically much smaller compared to the radiation imaging that we covered so far. Of course, it is also much lower than the beautiful modality that we will cover later, which is MRI. So, this is one of the inherent disadvantages, and another being it is very local. Remember we talked about whole body imaging in PET, whole body imaging in CT. Ultrasound is still very regional. You look at a target, you do abdominal imaging or you do heart imaging or you do surface MSK imaging, you do breast imaging, thyroid imaging, prostate imaging. So, it is very local, okay. That is one of the other disadvantages along with the quality. However, there are some medical imaging applications for ultrasound that are unparalleled. For example, imaging the fetus, right. So, baby inside the tummy, oh, you are not going to give radiation, all those things, it is all risky. Maybe MRI also, we did not cover it, but we have seen the photo of an MRI in our intro, right. You see the patient dust, or maybe you have seen it in person when you have gone to some imaging center. You have to go into that big tunnel, right, like your CT. So, that may not be that comfortable for the mom, right. So, imaging fetus is a very powerful application for ultrasound. Heart imaging, live beating heart you can see, right. So, that is another powerful. Echocardiography is something that you would have heard. There are several applications like that, but just the point is to bring out some of the things that you may be familiar with, right. So, looking at so this is non-invasive, right. So, you are looking at the baby inside the tummy by placing a probe on the outside. So, you can also see that this is regional, he has it on the hand and is moving around. So, this is a typical scanner. So, it is besides the patient. So, the patient can also see, right. So, these are the advantages, these are the new information that we are going to get using ultrasound, and let us jump in to really see more about what do we mean by this and how do we get this. What does this image mean from a physics point of view, right? What does this white mean? What does this black mean? What does this gray, right? Why is this black and white? What does it mean? Of course, we know the clinical, okay, this is nose, head, spine, that is fine. But from our physics point of view, what is the meaning of this color, right? What is a physical quantity? What is the units, right? Those are the things that we will try to understand, okay. So, before we go into ultrasound, it might be productive to recognize that ultrasound is just one type of sound. Okay, sound we are very familiar. So, we will start with what do we mean, our understanding of sound, and then perhaps get to ultrasound. Okay, sound is nothing but a mechanical disturbance. Okay, a mechanical disturbance, I have just put in bracket or bold few terms which we will go in detail. So, mechanical disturbance or energy that propagates as a pressure wave through a material medium. So, there are three key descriptors that are here, which we need to carefully understand. If we understand that, understanding sound or defining sound will become very formal. So, let us take what is the energy, right? Energy is capacity to do work. Okay. So, in that sense, what do we mean? Oh, it can essentially, sound energy can do back and forth displacements of object in its path. So, something that we are familiar when we talk about sound, we hear sound. So, what happens when the sound comes, when the pressure wave comes, right, the energy comes, right, when the sound energy comes, your ear drums are displaced. Okay. So, sound is a energy, energy means capacity to do work. So, sound energy can move back and forth a object that is in its path. In this instance, it is the eardrum that we can relate to. Okay. So, so there is a energy that propagates as a pressure wave. What do we mean by wave, right? We are all familiar, we use, this is not electromagnetic wave. So, this is the thing, right? We covered electromagnetic spectrum and we sometimes also called as electromagnetic waves, but then, right, we had radio frequency wave. So, we did not really microwave, but then sound, ultrasound, it is not going to be there in your EM spectra. This is a modality that is not there in the chart that we started out. Okay. So, this is different, even from the fundamentals of which engineering program background students are exposed, right. EM means electrical background students would typically be exposed to electromagnetics, whereas the moment you talk about sound, pressure, it is always mechanical engineering. So, you see the interdisciplinary nature of the imaging systems and more so ultrasound, starting with the fundamentals, right. So, wave is a propagation of this disturbance place to place. The real nicety about wave described here is in a regular and organized way. So, even though it is disturbance, right, it is a disturbance. Disturbance is usually used in a term of connotation of negative sense, right. Something is disorderly, disturbance means that is a, but the beauty about ultrasound wave that we are going to cover or sound wave that we are describing right now is that this disturbance actually travels from place to place in a regular and organized way. What do we mean by regular and organized way? That means as engineers, we are looking at it and saying, look, regular and organized means, can I use a mathematical expression to describe the wave, right. So, we are all very familiar with waves, right. For example, you throw a stone into the water, right, you will see ripples, you will see the waves that are moving here in the surface. So, we are all familiar with waves, okay. But what is the wave that we have described here? Oh, propagation of disturbance in a regular and organized way. So, when you throw this, you have seen the wave, right, you would have seen this, But the beauty that we look at is oh, not only we will describe, oh, you see the waves that are moving. We are engineers. What we will be able to do is, we will be able to write a mathematical expression, right, a mathematical equation, and say, oh, I can communicate, right, this wave in terms of this equation. Okay, that's why it's regular and organized helps us. Essentially it tells you can come up with a mathematical equation to describe this, but you know what a wave is, right. So let's jump in little more. The last part is going to be your energy wave, and the last one was material medium, through a material medium, right. Sound waves need a medium. See, this is the important, this medium has to have a material or molecules to travel. This is one of the first differences between what we have covered so far, electromagnetics, right, based modalities. There sound can, light can travel in vacuum, the EM can travel in vacuum, whereas in ultrasound, key difference is the fundamental signal, right, your sound wave cannot travel in vacuum, it needs a material medium to travel. That is the first take home message. This is something that is kind of overlooked, right, but this will play an important role. Okay, so this is our material medium. So clearly, how do you generate a sound wave? You need a material medium. So a typical example, right, you have drums, you tap it, you vibrate, that vibration, right, you can, it comes and it moves, the energy comes to your eardrum vibrates, right, you interpret that. So sound wave can be generated by vibrating objects. So you need a material medium, otherwise even if you tap, if there is no medium, there won't be any sound that will be generated. Okay, so this is an important idea. So if this is the case, how are the different ways, right, when we talk about what is, now we talked about sound waves, now we need to, our interest is ultrasound. Okay, so what is ultrasound? Same thing as sound that we covered, right, all the understanding that we did using sound is, ultrasound is just one specific class where the frequency, right, when we talked about sound, we talked about eardrum, we can hear. So the only difference is ultrasound, you have your frequency of the waves greater than 20 kilohertz. Why is that? That is beyond your audible range. So relate this to pitch, okay, shrill, pitch. So there are, so human beings it's 20 kilohertz. It's known that some of the animals, for example, have a higher range, audible range, right. So dolphins, they say, bats use ultrasound, even sometimes dogs can hear little higher frequency that we are not able to hear. So sound and ultrasound, the difference is ultrasound is just operating at a frequency that is beyond human auditory range, which is greater than your 20 kilohertz. So typically in medical imaging, right, you have several different applications of ultrasound, non-destructive, right, non-destructive evaluation that they do in engineering firms for quality check for steel or concrete, or the whole area of non-destructive testing or evaluation. If you are from mechanical engineering domain, you probably would have heard that. There also they use ultrasound, but typically it's on the kilohertz range, hundreds of kilohertz range. Whereas in medical ultrasound, typically you are talking about 1 megahertz to 20 megahertz. Okay, so higher frequencies. So much for ultrasound. So now we know what is an ultrasound. We kind of get what it means, but our objective is to slowly jump in and talk about mathematically describing this, right. So what we have seen so far, ultrasound also exhibits a general wave motion, right. What do we mean by general wave motion? It is a, right, ultrasound wave transport energy by setting molecules of the medium to oscillate back and forth. Okay, so there are several ways. There is a relationship between your medium, right. When you say medium, there are particles in the medium. The particles in the medium has to oscillate, right. and then a wave rides on it. So, there is an intricate relation between the motion of the particle and the wave that is moving. Okay. So, that defines the type of waves that are, there are different types of waves depending on the relationship between the particle motion and the wave motion. Okay. Simple way that you would have heard about generating a sound wave, right, your tuning fork experiments in your high school, right. You take that tuning fork, you tap it, it vibrates, right. When it vibrates, the particles surrounding the tuning fork also vibrates, and whatever oscillation this is happening, if you can hear that the vibration proceeds, hits your eardrum, and you interpret the sound. And you would have done different frequencies, tuning pitch, right. You will have different forks, each one will create a different pitch, right. That is what, so this is a easy visualization that there is a connection between particle vibration and the wave that is traveling. This particle is not coming and hitting your eardrum. This particle is around the tuning fork. That particle is not coming and hitting your eardrum that you are hearing. It is a wave that is coming and hitting the eardrum. So, the wave is transported, the wave travels because of the support of this particles that oscillate around its position. So, the particle does not move, right, it is moving back and forth in the same, around its same location. Okay, so that is the key. So, depending on the type of particle motion and the direction in which the wave moves, we can have different types of waves. Okay. So, pressure wave that propagates through the matter via compression and expansion of the material, right. That can have two different, there are several, at least two that we will recognize here, at least in this slide, and then move on with only one. So, one is longitudinal wave. A longitudinal wave is where your particle motion and the wave motion both are in the same direction. Okay. And a shear wave is where the particle motion and the wave motion are orthogonal to each other, perpendicular to each other. Of course, we will have a small animation to explain this, but there are several different motions. Surface wave that we saw, right. Surface wave is another type of motion where the particle is moving in one direction, wave can move in another direction. So, there are several different types of waves. We will focus on longitudinal wave, right, where the particle motion and the wave motion are in the same direction. We will ignore shear wave because our body, what is our body? Oh, we are mostly consistent of water. So, we are liquid body, 70% water. So, we are all fluid. Okay. So, essentially it will not support shear wave, or for all practical purposes your soft tissues are water heavy and therefore will not support shear wave. So, this kind of motion is not supported in biomedical tissues and therefore soft tissues, and therefore we will focus only on longitudinal wave. So, let us just take a couple of animations. So, what do you see in the top, right? Well, this is essentially kind of a piston, right. So, this is basically trying to move, this is a medium, these are all representation of particles in the medium. For an untrained eyes, what do you see? Oh, you will look at it and you will say, perhaps if you are thinking like most people, you look at, see, there is something that is going from left to right, right. There is motion from left to right. Oh, that is your wave. So, you can clearly see that the wave is traveling from left to right. Okay. Here I oscillate this, right, this red line, that is basically vibrating, moving left and right, and therefore the particles surrounding that are starting to move and you see a wave. But notice carefully, there is an illusion. If you sit at one particle, right, localize, take one particle and focus only on that particle is actually moving left, right, right, left, right. So if you sit on any one particle, you actually see that with the time, it is actually moving only back and forth. It is not going from left to right till the end. But they all are synchronously doing that you have a wave that is going from left to right, whereas the particle itself is only oscillating around its position back and forth. Here the direction of oscillation back and forth and the direction of wave are in the same direction. This is called as your longitudinal waves, compressional waves. Okay. So this is what we will exploit, right, in biomedical imaging, ultrasound imaging. Of course, the other one is your shear wave, transverse shear wave. So here why is it transverse shear wave? Look at the particle motion. Clearly you can see a wave is going from left to right, right. So you can just look at it, you see that the wave is going from left to right. But then you sit on this one particle, right, say let us take some, you go up, come down, go up, come down, go up, come down. So the particle is actually going up and down around its mean position, whereas the wave is going left to right, right, perpendicular to it. So this is a shear wave. So the particle displacement, the particle motion and your wave motion are on perpendicular directions. Clear? Of course, this, like I said, is not supported in the body for the soft tissue that we have, and so we will ignore shear waves. We will focus only on what we call as compressional waves or longitudinal waves. Okay. So we will only focus on longitudinal or transverse. So there is also a possibility of mode conversion. That is, you have one mode, right? You have longitudinal. When you have an obstruction, some of which can get converted to transverse, but we will ignore all those in our material, okay, because that is not that dominant in biomedical applications. Okay. So if you have to describe the wave, we need to have some wave equation, but before we set stage, we need to talk about an important descriptor for this wave, right, or wavelength. Okay. Wavelength or lambda, this is what we typically use. So you have regions of compression and rarefaction. So it is one cycle, you can measure it from wherever, peak to peak, trough to trough. What we are talking about is one cycle. Okay. So that is your distance between, or distance of one cycle is your lambda. Typically we get, so this is in length scale. Okay. Typically we get sub-millimeter. This is an important parameter because this determines your, this is very related to the resolution of the modality. Okay. And so this is very important. Sub-mm lambda is achievable in ultrasound. Okay. So now we will jump into talking about the wave equation. So we say let the acoustic pressure be P of x comma y comma z comma t. What does that mean? So from your everyday experience, you know, say for example sound, right? When you create sound, what happens? Okay, my voice box creates that pressure difference and it generates sound of a particular frequency. So a sound wave, and my mouth is the aperture, right? I am controlling the aperture opening. But the point is, a sound is traveling. Inherently what is happening? It is 3D. Unless I make an effort to make it go in a particular direction, right, it is going to be 3 dimension. That is, the pressure wave is traveling in 3 dimension. So if I have to describe the wave, then I need to describe the pressure changes in x comma y comma z and also with the time, right. So it is changing with the time. So that is what we saw in the wave, right. The wave, it compression, rarefaction. So but you sit at one location, you are going compression or rarefaction. So it changes in space and time. So let the acoustic pressure, we will denote it as P, which is a function of x, y, z and t. So given the introductory nature of the material here, we will not go into derivation, but it is from the physical properties of matter. So, we could relate this P, right, we could describe this P, this in 3 dimensions using a 3D wave equation which will be of this form. What is this? Oh, this is your Laplacian spatial derivatives, right, second order. So, dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So, this is your Laplacian. So, your pressure is changing in space and time, clear. So, your pressure is changing both in time and space, that is what we saw, right. You saw the wave travelling from left to right. So, if you freeze 1 minute, right, one instance, each location has different pressure, some experiences high pressure, some experiences low pressure, right. And if you freeze time, right, then you see same behavior. So, both the time and space or the pressure is oscillating or it is changing. So, you have, if you have to describe this pressure, it is changing both in time and space. So, you can you get this wave equation that captures both the change in space. Of course, here we have 3 dimensions. So, we put the space as x square, y square and z square and time. So, what is this? This we will talk about it little more detail, but this is your, we talked about wave, we need a material, right, medium, a material medium for wave propagation. So, this has to do something with the material medium. What is this? This particular thing written as c is your speed of sound, because c we use even for speed of light, right. So, c is kind of velocity. So, here c is velocity of sound, okay, velocity of sound in that medium. So, this is actually a material property, we will talk about this in a bit, okay. So, this is your 3D wave equation. However, like we said, this is fine, this is all powerful, neat, but then we are interested in making life easy with context of the application, which is biomedical imaging. So, in our case, even though 3D is there, we will try to look at waves, at least 2 different types of waves that are applicable for imaging. One is your plane waves. In plane wave, what is a plane wave? Oh, the waves that we talked about, 3 dimension x, y, z, pressure is changing. We will talk about in a particular plane, it is all of the same pressure, right. It is changing only in one direction. So, we will talk about 1D wave equation, that is the wave is travelling only in one direction. In this case, we talked about in the z direction. So, the wave is moving in z direction. So, in the xy plane, right, in the xy plane, all the points, all the particles in this xy plane experience the same pressure. So, this, right, this is moving back and forth. So, the wave is moving left and right. In plane waves, what we talk about, plane waves, we are talking about the planes that are moving, okay. That means all of the particles on this plane experience the same pressure, okay. So, we will consider only 1D wave equation, 1D wave, especially longitudinal or compressional wave. So, this is a setup, right. Why we are not going to derive, but just want you to have a look at the schematic, how we set the problem, and then we will straight away write the equation. In fact, we have the equation, right. We will just list it for the dimension that is described here. But what you will see here is, you could have, these are the particles, right. So, you could have increased pressure, decreased pressure. So, that means the pressure is changing in z direction. So, we will have one pressure at one location, another pressure at P of z plus delta z. So, there is a differential pressure. So, there is this velocity of the particles. So, particles have a velocity, right. Of course, you can then particle, then you have a cross section area. Remember, we are talking about planes. So, cross section area through the volume through which this is happening. So, this is your area, right. Z is the direction of our motion. Of course, then you can write your mass in terms of density area delta Z. So, volume A into delta Z is your small volume, rho is your density. So, density into volume gives you mass. So, we could set the problem up like this, right. We are not going to derive, but if you use the first principles of conservation of mass and conservation of momentum, you will be able to get to this equation. So, this is nothing but x and y are gone. So, this is one dimensional, the wave is travelling in z direction. So, this is dou square p by dou z square, right. So, dou square Laplacian we had x and y, that is gone. We are considering only the wave in one dimension along the z direction, and therefore, your pressure is changing only in z direction. Dou square p by dou z square equal to, right, 1 by c square we had dou square p by dou t square. So, I have bought that RHS to LHS. So, it becomes dou square p by dou c square minus rho naught k dou square p by dou t square. Of course, when we did the general thing, we talked about here what was there, 1 by c square was there, and I said it is related to medium property. So, this is actually medium property, right, average density of the material, and then this is your compressibility of the material, right. Particle is, you are applying pressure, it has to move. So, how compressible, right. So, compressibility of the material and the density of the material will determine the propagation of this wave. Okay, clear. So, this turns out C is your, because we had, remember, in our general equation we had 1 by c square. So, essentially C is 1 by square root of rho naught k. So, we are not deriving any of this given the introductory nature, but essentially you see that the wave equation that we are going to deal with, the 1D wave equation that we have dealt with, is dependent on the material, right. The material property of density and compressibility is related to C. So, if I say C, that is velocity, speed of sound, that is actually material dependent. Okay. So, that is a very important aspect. Okay. So, we have this equation. What is our interest? What this says is a medium, right, a medium can support a wave propagation. If it supports, this equation will be satisfied. But what can be P, right? What is your P? Oh, this is just an equation. I need a solution for this equation, right? I need to have a P. So, what is a solution for this equation, or in other words, what is the pressure function or pressure waveform that can actually propagate in this medium, right, satisfy this equation. So, solve this, you can have a general solution. The general solution for this can be written in terms of P of z comma t, right, because we are dealing only with the z direction. Pressure at any z comma t has either a general function of this form, which we have a suffix or subscript here as f, meaning forward direction, or b, backward direction. So, these two are independent, each of them can satisfy the solution here of this form. So, general function which is having t minus c inverse z. So, this is called forward travelling y. Oh, if you take the general equation, it is 5z of this thing, right, cz, right, it is a function of c inverse z. So, at t equal to 0, so as t increases, what happens? Oh, you travel in positive z direction. As t increases here, you go in the negative z direction, and therefore, this is called as forward or to the right, right. So, this is called as your forward propagating wave, and this is called as your backward propagating wave, because the basic function phi of f, basic waveform, is function of, right, basic waveform at t equal to 0, right. If you reference that, this term is moving towards the right. So, this wave is moving in the positive z direction. This wave is moving in the negative z direction as t increases, and therefore, it is positive forward wave or backward travelling wave. Okay. Of course, we are interested, since both of them can independently, they have to satisfy, we can treat one to be, one of them is identically 0. So, essentially we will drop the backward. So, we are interested in sending a wave into the tissue. Okay. So, therefore, we are interested in the wave that is going into the tissue and it can come back. We are not really interested in when the wave is generated, one goes into the tissue and one goes the outside air, right, or the other direction. We are not really interested in that, and therefore, we could, without losing the generality, we can treat only one term here, one solution here, one general solution here, which is of this form. Okay. So, what could be an example solution, one solution of that form? You could have any form, right? Anything of this form is a solution. One typically used solution is the harmonic plane wave. What do we mean by that? P of z of t is cos of kz minus k of z minus ct. So, you could have a delta function also. Okay. You can have any function, you can have a triangular waveform, you could have a square waveform, anything that satisfies this equation, right, but typically we use a cos. Okay. So, when you have this, what are the interesting relationship that we see? We have, this can be a solution to the equation if the argument, right, it has to satisfy equal to 0. So, what we can do is, we can first get a, if this is the solution, let us get the meaning of what is happening. If you sit, right, viewed at fixed particle. So, if you are sitting at a particle, then what is happening? The pressure changes in time, right. I sit on a particle, we are interested in only compressional waves. So, what is happening? I am moving left and right, back and forth along the direction. So, if I sit at one particle, with the time I am moving to the left, moving to the right, or rather I am having compression, high pressure, low pressure, right, that is what I am experiencing. So, fixed at a particle, the pressure changes in time, and what is the frequency? Frequency of this oscillation in time, right. So, that is your temporal. So, Ft is kc by 2 pi. So, this is your time quantity, this is your z is your spatial quantity. So, when you are talking about a particle, the particle is not moving in space fully, right. The particle is oscillating about its location with the time. So, you have a frequency of oscillation, which is your f suffix t, which is kc by 2 pi from here, right. Okay. So, then what happens if you are looking at it from a space point of view, viewed at a fixed time, right. If I freeze the time at one particular instance, then the pressure change in the z, right, there is a pressure, rarefaction, compression, rarefaction function, it is moving. When I hit the still button, froze it in time, you would have seen some location will be high pressure, some location will be low pressure, and essentially it is going to be a cyclic form, right. And therefore, you have what is called as f suffix z, which is your frequency or spatial frequency, right. So, your f suffix z comes from kz here. So, it is k by 2 pi. What is this k? This is an important quantity, it is called as your wave number. So, this we are very familiar, Ft we are very familiar, every one dimensional signal we talk about time as the index, right. So, therefore, frequency we always say cycles per second, so very familiar with that. Whereas, now we are dealing with spatial quantity. So, f suffix z is defined as k by 2 pi. What is this k? K is your wave number. Let us just complete this and I will explain you one more time. So, wavelength, which we saw. So, why am I talking about wavelength? We are talking about here Fz, we are talking about fixed in time, the pressure changes in z with frequency. So, pressure changes in Z one cycle is what we called as wavelength, right. So, therefore, there should be some relationship here. So, wavelength is the spacing between peak or valleys at any time. Now, I am saying Fz is the frequency. So, naturally these two should be related. So, lambda is nothing but 1 by Fz, which is 2 pi by k. So, lambda is your wavelength, this is your wave number. So, we can actually think about wave number k is equal to 2 pi by lambda. So, wave number, what is wave number? Wave number is, if you think about it, if you treat, it is all distance quantity that we are talking about. So, 2 pi, if 2 pi is the distance, right, lambda is also a distance, right. So, number of lambdas that can fit in 2 pi distance is your wave number. So, number of waves, right, number of waves, one wave, if you want to call that as one wavelength, one wave, right, number of wavelengths that are there in 2 pi distance, that is your wave number. Number of cycles that are there in 1 second is your cycles per second, your frequency here. Number of cycles, right, we also have time period 1 by f, right. What is the time period? The time of one cycle. So, there we call it time period, whereas in length scale we call this as wavelength, one cycle in distance, and therefore, your wave number is an important concept. It is number of wavelengths in 2 pi. Okay. So, of course, we can also then relate, right, these two. Okay, I do already see that I have lambda is equal to 2 pi by k, but what is k? I can look at here and say, look, k is nothing but 2 pi f by c, right. K is 2 pi f by c. So, 2 pi f by c will become top. So, 2 pi cancels, this is your, we know this from before. In electromagnetics also we related this, c is equal to f lambda, right, same relationship. So, you get that generic c is equal to the wavelength, speed of sound and frequency relationship is very similar to your electromagnetics. Okay. However, the interpretation, right, the interpretation is going to be different here because the wavelength, the c is a medium dependent property. Okay. So, if I increase or decrease frequency, what will happen? In a given medium, the medium is not changing, the wavelength will adjust itself, right. Wavelength will adjust itself to maintain c as a constant. That is a very important take home message. Okay. So, why are we interested in this solution? These are very widely used in ultrasound imaging. So, typically we send 3 or 4 cycles of cosinusoid, right, that is what we send. And so, given ft, the wavelength depends on c, of course, which in turn depends on the tissue property. So, this is the key. You can send any frequency from outside, you can generate the sound and send inside, but the speed depends on the material property, and the speed, that material determines also the lambda. A typical wavelength, right, for given configuration, say I have a frequency transmitted is about 3.5 megahertz. Remember we said 1 to 20 megahertz, but 3.5 is a very in a range that is very popularly used. Okay. So, 3.5 megahertz is f. If you send this and assume the medium to have some speed of sound which is 1540 meters per second, is a very common velocity that is that most scanners are calibrated. So, ft is this, c is this, what is your lambda? 0.4 mm, meaning sub-millimeter I said right earlier. So, this is 0.4 mm. So, this is very important factor because lambda turns out to be determinant, right. This is closely related to the resolution capability of the system. So, in what is the C of electromagnetics? Oh, 3 into 10 power 8. Okay. So, what will be your lambda? Orders of meters, right. C is equal to f lambda, that is what we have used here also. C is equal to f lambda, I know C, I know f, what is my lambda? It turns out to be 0.44. So, the speed of sound, because it requires a medium and the medium supports certain speed, this makes it a fortunate circumstance that the lambda is 0.44. If C is speed of light, you have meters, right, your lambda will come in meters, right. You do not want to image inside the tissue with meter resolution, right. So, clearly this is a very fortunate circumstance that the speed of sound inside the tissue is only 1540 meters per second, and therefore you could use some typical megahertz range and get a wavelength that is small enough, as in compared to the dimensions of the objects that you are going to. So, the resolution is closely related to your lambda. Okay. So, now we will jump back to the 3D equation. This is in coordinate system that we use x, y, z, Cartesian coordinates. Clearly the wave equation can also be described in another coordinates. A natural coordinate that is very intuitive and very mathematically straightforward is your spherical coordinates, because I am talking now, the pressure wave is going in all directions, right, up, down. So, it is actually in that sense, if you look at it, my voice box is a point source. It is sending waves in spherical all directions. So, it may be a lot easier to describe this wave in the natural coordinates of x, instead of x, y, z, of radius. So, this is 0, 0. All I can say is the pressure is changing in the same radius, is the same thing, right. So, I could write P of r comma t instead of x, y, z. So, r will be your square root of x square, y square, z square, right, spatial coordinates. So, if you do this, we can manipulate our wave equation that we had before, write it in spherical coordinates like here. Okay. So, if you it is very similar, right hand side is actually no big change, your pressure is changing with the time, changing in space and time. So, you get the second order. So, dou square p by dou t square 1 by c square. So, there is no change here. Here instead of x, y, z, the Laplacian that we had, we have written it in terms of just r. So, 1 by r dou square by dou r square rp. So, if this is the wave equation in spherical coordinates, what will be a solution? Solution can also be of this form. Pressure of RT will have two general solutions. One is, what is O here is outward, right. So, when the waves are going, right, it is expanding and shrinking. You can think about expanding and shrinking. When it is expanding, so you can have a wave that is going outwards, right. What do we mean by outwards? Your radius is increasing here, or inwards, your radius is close. So, in practice what is going to happen? Your inward wave is not that intuitive, and it is not, we are not going to encounter that physically, and therefore, what we are really interested is in the two general solutions that you have, it is the outward propagation that will be used. Okay. What is one difference between what we saw in the xyz coordinates and this thing? You have a 1 by r term, right. So, with the distance, with the distance, the pressure actually, the amplitude of the pressure drops down linearly 1 by r. So, that is something that we need to keep in our mind, back of our mind. When it comes, we will recognize that. Okay. So, we will deal with P of r comma t in spherical coordinates. You can write it as 1 by r of phi naught t minus C inverse r. Clear? So, why is this important? This is important even though we may want to start with only plane waves. Given the wave, so now we know how to describe the waves, right? That is what I said, organized, because now I do not have to visualize anything. I can just write this equation and the equation captures, right? Mathematically it completely defines the wave. So, the natural extension is, in our understanding, if I can understand this wave, what happens to this wave when it is sent into the body? That is the key. So, I want to send the wave into the body and the wave has to interact with the body, and I have to capture the waves that are coming out of the body after the interaction one way or back, right? We had the through transmission or on the same side, right? That subtle difference we will make. So, first is you have wave, we are able to describe the wave. Now, this wave has to interact with the tissue, which will be our next focus of attention. And then we will talk about the configurations, whether you want to send the wave from one direction and detect it on the other side, or you want to send in one direction, receive it in the same direction. All those nuances we will talk about. Okay.